Hey students, this is lesson 5.2, perpendicular and angle bisectors. We're going to use properties of perpendicular bisectors and angle bisectors to solve problems. Go ahead and do this review. I'll check back with you. All right, so here's the theorem we're going to be using. A couple of theorems. The point is on the perpendicular bisector of a segment that it is equidistant from the endpoints of the segment. So in this one, if PM is perpendicular to AB and AM is equal to MB, then PA is equal to PB. And then the converse, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So this would be on a line perpendicular that bisects RT. It would look like that. All right, so let's use that. What is MN? Actually, MN is a line segment, but let's see, we want to know the length of MN. And we know that MN is equal to MP, and that's by the perpendicular bisector segment. So we can substitute 6x minus 1 and 3x plus 8 for each of those. And then we could use the subtraction property of equality and subtract 3x from both sides. We would get that. Use the addition property of equality, add 1 to both sides, and we would get that. Divide, and we get x equals 3. And then we're given that MN is equal to 6x minus 1, so we can now substitute 3 for x, and we get MN is equal to 17. All right, you go ahead and try one. All right, using the perpendicular bisector, the monkey bars are located midway between the slide and the tether ball. Let's just make a little notation there. Which of the following are about equidistant from the slide and the tether ball? Well, using the perpendicular bisector theorem, we know that anything that is on the perpendicular bisector would be equidistant. So if I were to draw a line on those monkey bars and make sure that this line is perpendicular and that it's true that the slide and the tether ball are equidistant, then anything on that line needs to be equidistant from both the slide and the tether ball. So what I'm saying is this distance here and this distance here are the same. So, and it appears that 4 squared is on the perpendicular bisector, or at least is near that. Let's say is near the perpendicular bisector. Therefore, it is, by the perpendicular bisector theorem, it is equidistant. From the tether ball and the slide. All right, you try it. All right, a couple more theorems here. The distance from point to the line is the length of the perpendicular segment from point to the line. This distance is also the length of the shortest segment from the point to the line. So if you want to have the shortest segment to a line, you need to be on a line perpendicular to that, from that point to that line. And if a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. Now, when we say that, that's where this perpendicular line comes into play. We're talking about the shortest distance. So, if point S is on the angle bisector of angle PQR, then SP is equal to SR. And the converse of that, if a point in the interior of an angle is equidistant from the sides of the angle, that shortest distance again, then the point is on the angle bisector. So point S is on the interior of angle PQR. If SP is equal to SR, then S is on the bisector. All right, so let's use that. What is the length of OP? So we're going to say that MN is equal, or MO is equal to OP. And that's by the theorem we just talked about, the angle bisector theorem. And then we can substitute and we get 6x is equal to 3x plus 12. Subtracting, we get 3x equals 12. Dividing, we get x equals 4. And we know that OP is equal to 3x plus 12. That's given. And by substituting 4 for x, we get OP is equal to 24. All right, go ahead and fill in the steps here. All right, that's the end of the lesson. Go ahead and do the lesson check, and we'll talk about that next time we meet in class.